Good afternoon, everybody. Welcome to our webinar. I'm Bob Lazaro, Executive Director of the Northern Virginia Regional Commission. For those of you who are not familiar to us, we are a consortium of the 13 leading local governments in Northern Virginia, representing about 2.5 million residents. I'm pleased to be joined by my colleague, Dr. Dale Medeiros, a Senior Environmental Planner here at NVRC. As you all know, Northern Virginia has the highest density of data centers, not just in the United States, but in the world. And NVRC is fortunate to be able to take a look around not only the country, but the world on alternatives and opportunities to help people understand what alternatives are out there. And today we're pleased to be able to have Alan Schur from Enchanted Rock to present on how microgrids can help localities on data center and other critical infrastructure energy challenges. This webinar, once again, is being recorded. We ask that all questions be put in the chat, and I will then, at the end of the presentation, read them back to Mr. Schur. Again, the slides and the recording will be made available on our website tomorrow. They will also be posted on our LinkedIn page today. And with that, Alan, I'm going to turn it over to you. Thank you for being with us.
Yeah, thanks, Bob, for having me. I'm excited to share some of our experiences and provide some perspective on energy challenges related to data centers. It's true, Northern Virginia is really the epicenter of data center development, and what you saw in the past few decades is just going to continue and even get more aggressive in the form of data center development. Enchanted Rock is a microgrid developer, owner, and operator. We're based in Houston, Texas, and we do have a facility operational in the Quantico area where we're on the base there providing backup power for some critical infrastructure on that base. But data centers are what we're here to talk about today, and the energy challenges that are coming from those data centers. We'll go to the next slide. The challenges are really shown here in this graph. This is a forecast of the Virginia load growth zone, looking at historical actuals and forecasts that have most recently been updated just recently to show even more aggressive growth. 11 gigawatts is the growth forecast over that time horizon. And a gigawatt, for those of you that don't build power plants for a living, a typical large power station is somewhere usually between 600 megawatts and a gigawatt. These are the very large power stations you might see out on the horizon sometimes. That amount of load is just staggering. A lot of it's being driven in the data center community by artificial intelligence and the need for substantially more computing power. But with the Northern Virginia market leading the world really in data centers, everyone in the data center business typically has and is trying to grow their campus in Northern Virginia. Second point here, of course, is that data centers need backup power for the improbable circumstance where the power goes out. Their customers expect, their own operations expect to have continuous flow of energy. So they typically do this with on-site diesel backup generators that don't typically run very much. When they do run, either in testing, which they are prone to do either monthly or bi-monthly, or when there's some kind of a power outage, they do operate, and the environmental footprint from those diesel generators is pretty substantial. They don't operate very often, so it's kind of an accepted trade-off. In the Northern Virginia non-attainment area, the equivalent of clean diesel is what has been called for in the most recent data center development that reduces some of those emissions to some degree, and I'll show you a chart in a moment that quantifies some of that. Let me just finish the last point here. The this 11 gigawatts of new diesel generation is going to create even more concern, I think, related to the air emissions, carbon emissions, and overall environmental impact of data centers beyond land use and transportation and things of that sort. Now we'll go to the next chart. So I want to talk about microgrids as how they satisfy that same resiliency need and do more. Let's go ahead. I want to just draw a comparison between a diesel backup generator, which is the standard for 99% of data centers, really, and what Enchanted Rock provides in the form of a natural gas generator that can have substantially improved environmental attributes. To start with, the diesel generator has an incredible technical performance standard. It is a terrific piece of equipment for purposes of providing backup power. It starts really quickly, less than 10 seconds. It can carry a variety of different load types and maintain utility grade power, even when not connected to the grid. That's a very significant engineering challenge that diesel has been well tuned to do. If there is to be a substitute for diesel generators, it has to meet those technical standards or it won't be accepted. That's a commercial reality. We've done some interesting things in packaging our generators up so that natural gas generators can match up to those diesel standards. That's not common in natural gas generation, I should point out. It's taken some extra engineering steps to do that. With that said, then you get into a lot of other attributes that either are requirements or nice to have in the form of improvements over how diesel operates. We also can't take up more space. Space to a data center is really valuable. They want to have as much compute power on a particular site. And so if the mechanical plant, that is the backup generation, the chillers and other things, take up more space than their current designs, that takes away from their ability to build more space. We can match that power density. In the same footprint, we can have the same power output. We're also much, much quieter. 68 decibels versus 75 decibels in the decibel scale. 68 is normal conversation. 75, you have to raise your voice. It's what you might hear on an airplane. And often significantly higher than that. And if it's not with a sound enclosure, you'd have to have ear protection in order to be around that equipment. Now let's talk about some of the other attributes like local emissions. As I mentioned, the cleaner diesel that is required in Northern Virginia, that's known as a Tier 4 or Tier 4 emission standard, even if it's not an actual Tier 4 certified engine. It requires an enhanced emissions control package in order to get those emissions lower. Whereas starting with natural gas, you don't need that same enhanced emissions control. SCR stands for selective catalytic reduction. It's a more complex system for removing pollutants, whereas natural gas can be 10 times cleaner than that clean diesel that I mentioned, or even 100 times cleaner than typical diesel generators, many of which are already in operation in Northern Virginia. Can we reduce carbon further? Now, these don't run very often, so the carbon isn't significant, but it is a positive, and it can be reduced in the form of diesel if you use some kind of a diesel blend. Vegetable oil or renewable diesel blends can reduce but not eliminate the carbon from the use of those fuels, whereas with a natural gas engine, you can go zero or negative greenhouse gas based on renewable natural gas. And I'll just pause for a moment and tell you what I mean by that. Renewable natural gas is the capture of naturally occurring methane release from things like landfills, dairy farms, food waste, ag waste, water treatment facilities that, left to their own devices under normal operations, methane is a byproduct of the decay of those organic materials, and it's released into the atmosphere. Methane is a much more potent greenhouse gas than carbon dioxide. And so capturing it, cleaning it up and putting it into a pipe, a natural gas pipe, it looks like a methane molecule that can reduce methane release. And indeed, it can provide a zero carbon fuel, offsetting the use of fossil natural gas with renewable natural gas. It's a large and growing industry. It's used a lot for transportation fuel, but it can also be used to offset all of the greenhouse gas emissions of backup generation at data centers. With fuel security, another attribute we often talk about with data center operators, they do have on-site storage. That's the good news. They have fuel right there where they need it, but they are limited to what they have on site. And for extended outages, the situations where the grid really is having difficulty during particularly extreme temperature conditions, or if there's some other catastrophe on the grid, they have a difficult time getting refueling during those emergencies. So difficult that you might as well assume that it's not possible. Whereas the underground natural gas infrastructure, far more reliable. It is incredibly reliable statistically because of continuous fuel delivery. You can run these gas microgrids for an extended number of days to weeks. We have a customer that just asked us yesterday to run for the next 8 days. And it's a flick of a switch. We don't have to worry about replenishing fuel supply on site. Then finally, and this is a super important point, to support the grid beyond just power outages, a microgrid can provide an additional value stream that generates an economic revenue stream. Diesel generators have a very difficult time, if not impossible, to run additional hours. And I think in Northern Virginia, there was the request last summer to be able to run additional diesel generation in order to support the grid. And it was met with a lot of resistance because of air issues, air emissions, whereas a natural gas generator with the clean emissions that I described before can run very easily, well within emission limits, and provide those selective hours when the grid really needs support from the load side by taking load off the grid during those periods of time. That's just an overview comparison. I think it's important to note that there is a commercially viable alternative to diesel backup generators, and I'll talk about some case studies here after a few more slides. Let's go to the next one. This is the emissions comparison that I talked about before as a percentage of Tier 2 diesel, Tier 2 being the normal standard for diesel generation. Tier 4 is what is required in Northern Virginia because of the non-attainment. And you can see that Tier 4 is a pretty significant improvement over Tier 2, yet you can do better even than that. And Enchanted Rock's color, that kind of cyan color, shows you in volatile organic compounds, in NOx, in carbon monoxide, in particulate matter, and other, the sulfur chart there is a little bit misleading. There's really not much sulfur in natural gas, but that is an allowable level for the EPA. But you can see the emissions benefits compared to Tier 4 or Tier 2, of course, are significant. And that allows for a lot more flexibility for these kinds of units to provide services back to the grid. Let's go to the next chart. There's another challenge that's facing data centers as they're trying to grow, and that is that they're having a difficult time getting service from utilities. And I think in Northern Virginia, you all are probably well aware of the delays that Dominion has had in connecting new data centers. It's a challenge, at least because getting the equipment to build substations takes usually 2 to 3 years to get that kind of high voltage equipment. It can be longer if there's transmission lines that have to get built. And so data centers are really constrained in their ability to grow while they're waiting for that service. And usually there's about, let's just say for the sake of this example, maybe a 36-month period where the utility interconnection is taking place. And the data center has to wait then 3 years before they can get connected. And then they have utility service is completed, and the utility is providing primary power. That's today's normal course of business for a lot of data centers looking to expand. The microgrid that I described before can also provide a bridge power solution so that that data center can be operational sooner, generating tax revenue sooner. During an 18-month construction period, the microgrid can be developed and provide primary power. We call it a bridge power solution because it's bridging between no utility power and when utility power is fully available. That same microgrid on site can provide bridge power during that 18-month period and then revert into backup power only along with grid support once utility service arrives. I should note that those grid support functions are generally in the neighborhood of 100 to 200 hours a year, where the grid really could use some assistance without building really large power plants to provide that few hundred hours a year. These microgrids can provide those grid services. And of course, backup power, which is a difficult to forecast number of operating hours each year. So this approach to bridge power can accelerate the time to construction for data centers, and it can therefore help them generate more revenues themselves, more tax revenue for local jurisdictions. Let's go to the next chart. So that's really the context for data centers and the problems that they're facing and some of the alternative solutions. Let me give a little bit more detail here about how we do what we do. We are a resiliency and a grid stability service provider. That's really the core function. These microgrids perform two purposes, kind of like an Airbnb. It can be your vacation home and you can rent it out when you're not there. This is a backup power plant, local resiliency, as well as grid stability services. When the power is on, it can still provide support to the grid and can integrate on a local basis on site a variety of different resources. Generation, of course, maybe could have some renewables and storage on site. Those are not very common in the data center world because the power loads are so enormous that providing any significant contribution from local resources is difficult. But in other types of applications, critical infrastructure, that certainly can be more common. And we can integrate all of those together with a microgrid controller that manages during both outages and non-outage conditions, all of those assets, so that we can provide reliable power to the customer and these services back to the grid. Let's go to the next chart. The reason that this isn't such a common practice is that backup generators are pretty low cost. For data centers, they're a standard cost of doing business, and this just gives you a relative scale of the price of tier 2, both from a capital expenditure standpoint plus an operating expenditure on a net present value over 20 years. The net cost of backup power would be indicated by the top of that bar on the left. For tier 4, it's more expensive. It's more expensive mostly because of CapEx is being higher. That extra pollution control just adds cost to the generator. It also is a little bit more expensive to maintain every year. A natural gas microgrid is more expensive yet. The capital equipment for a microgrid is higher, in part because natural gas is inherently more expensive per kilowatt of output or per megawatt of output than diesel is, because it's got you need more displacement in order to get the same power output. And all things being equal, no one would ever put in a gas microgrid because of the CapEx and OpEx being higher than even tier 4 diesel. But these grid revenues are so significant because the grid is really desperate during certain times of the year where they need to have the ability to call on capacity and dispatch it, and price for having that flexibility is quite high, that when you net those revenues out over a 20-year net present value, we can create a net cost of resiliency that is lower than tier 2. It's a really powerful mechanism. Again, back to my Airbnb example, it's a significant amount of supplemental revenue for an asset that would otherwise be sitting idle much of the time. And that lower cost of customer resiliency, the ability to have cleaner emissions, and the ability to have a more reliable fuel supply, we think that microgrids are how data centers in the future will need to operate in order to both manage their own requirements and then support the grid and local communities. Let's go to the next chart. Some quick stats related to our portfolio here. Very fancy flybys there. We have about 300 operational microgrid sites around the country. We have a lot in the Texas market. That's where we started. But we are operating also in Mississippi and Louisiana, Virginia, as I mentioned, in the Chicago area, also in California. We're up to almost a gigawatt now in total contracts. Of those 319 megawatts listed here in the lower left that are under construction, about 200 of those now are fully commissioned in the last 6 weeks or so. So we're now nearly 900 megawatts of commissioned microgrids. We have a lot of experience with this technology, a lot of experience working with a variety of different site conditions, and the statistics that we have related to the reliability of our systems show this 5 nines of combined reliability when we look at the grid, plus our ability to cover outages. It's really extraordinary. It's better than diesel performance. And we do that because we've had a lot of experience with utility outages, over 11,000 hours of utility outages at these 300 sites or so. Let's go to the next chart. Some pictures here to show a little bit more about what we do. I'm going to talk about each of these examples just to give you a flavor of it. Let's start in the upper right corner for a moment. This is a water pumping plant in Houston, Texas. The city of Houston is our customer. They move a significant amount of surface water around the Houston metropolitan area as a supplier to many other municipal utility districts, and they need to back up these pumping stations against a potential grid outage, either locally or at the system level. This is a 33 megawatt microgrid, and I use this picture first because it shows the construction approach that we take. There are 75 separate generators at this site. Each of those white boxes is a separate standalone generator that's not electrically connected to any of the others. And it allows that 75 megawatt or 75 generators to operate at a very high reliability level. In the foreground is the gas metering and pressure step down skid. And then there's transformers and electrical controls on the upper left of that site. That site's now fully operational. We installed all of those generators in one weekend with one crane, very much like Lego blocks, dropping them onto a steel base that we install first. On the left-hand side, this is the city of Chicago. ComEd is the utility that serves that area, and they are our customer. We're providing a community microgrid that is supporting an area of the south side of Chicago that serves about 1,000 customers, mostly residential and small business, also the Chicago Police Headquarters. And that's going to be used for emergency purposes when there's a grid outage to the area. The difference in shape of those units, there's a winter package that sits on top of our generators and keeps ice from accumulating in the generator. The lower right, we have about 200 sites that we serve grocery stores and grocery store warehousing. A little bit more of an up-close view of the generators. They're 12 feet high and 8 foot by 10 foot in plan view. So they're very compact footprint. That's a combined, those 3 generators combined for about 1.3 megawatts of backup power for, in this case, it's a grocery chain that is headquartered in Texas. And then let me talk about the Microsoft data center. The Microsoft data center is probably the one that is most apropos for this particular audience, of course, but we've been in contract with Microsoft since 2022. Our operation date looks like it might even now slip to 2025 because of delays on construction by Microsoft. But this project is the first of a kind in a number of different ways. It's the first natural gas backup plant that Microsoft's ever done. It's a 96 megawatt project, of which the first phase is 60 megawatts. And importantly, it is a dual purpose microgrid. It does provide backup power to the Microsoft campus, as well as support the grid when there's an electric emergency event that is called in California. There's a specific program that we're participating in that's part of the utility out there by the name of PG&E. But importantly, we're also using renewable natural gas for the first time. It's a zero carbon resiliency plant for Microsoft. Those renewable natural gas offsets will be purchasing natural gas from a production facility in California. It will in turn feed the pipe with the renewable natural gas that is captured from ag waste. And we will take credit for those offsets of renewable natural gas so that the gas that is consumed on site for either testing or backup power or for the BIP, base interruptible program, the demand response program from the utility, which requires renewable fuels, all of those hours of consumption will be offset with sufficient renewable natural gas offsets so that there'll be no incremental fossil combustion on that spot. It is more cost effective than Tier 4. And it's a very exciting project for us because of its being first of a kind, and also because many data centers look to Microsoft as being the leader in environmental commitments for their renewable purchases and for their commitment to get off of diesel generators by 2030. This is the first one that they've done that's sooner than that. So we hope to replicate it a lot, and we're in conversations with a lot of data centers about a similar kind of example. Let's go to the next chart. This is a bit of a summary chart here where I think we can cover each of these quadrants to talk about some of the advantages. But a microgrid is really a valuable asset for a community because for providing the kinds of grid services that are needed, it has a lot of land use advantages over things like solar and storage, which frankly are important parts of the overall mix. But for purposes of backup power, they take up so much space that they're really best sited at a utility scale, not trying to be on top of a data center building, but in fact, where the land is more conducive and less impactful in an urban area. It takes hundreds of acres to match up, say for a 100-megawatt data center, hundreds of acres of solar just to meet the noonday peak. And then, of course, storage on top of that so that you can spread that solar production over 24 hours. It would be thousands of acres for that same 100 megawatts. The visual impact of having these microgrids, it really disappears behind typical concrete walls, as an example, or fencing. Very low noise pollution, and they're not running very often to start with, even for backup mode or for grid support services, and there's no local water usage. So they really are a valuable attribute and environmentally less impactful than a lot of other options. I mentioned earlier in the upper right-hand side, the air quality benefits, which I've talked about quite a bit. It also reduces a lot of diesel emissions. Even the testing functions of diesel emissions can create issues with local communities, residents that are nearby or downwind. I'm sure they would welcome a reduction in those kinds of emissions. On the lower left, because of some of the benefits of grid services, during major outage events, a lot of customers might otherwise require their own generation. And there's a lot of risk associated with residential users of backup generators. Sometimes they get carbon monoxide poisoning or they have fire risk from refilling. Since we can provide local services to the grid and reduce some of those system outage risks, there's a lot fewer instances where local consumers or even small businesses might need their own backup generation, since the grid would be more reliable. And it reduces the burden on emergency personnel during these big emergencies. And we've had some of those emergencies around the country, although Northern Virginia hasn't experienced them recently. It was pretty close during Winter Storm Elliott a couple of years ago. reserve margins were quite a bit lower. And then finally, it does support local communities in the form of economic development. It can reduce the impact of these grid constraints by interconnecting, as I mentioned with bridge power, customers earlier to the grid. They can find these local communities more attractive for their investment if they know they can get electric service sooner than waiting these multiple years. In some cases, some of the largest loads are seeing waits of 7 to 10 years to get connected, and it's very difficult to plan capital investment for manufacturing or other kinds of industries if you have to wait that long. And it is just a much cleaner, more reliable system that we also think differentiates communities by having higher levels of reliability on the grid locally. So we think that these microgrids should be a considered tool in the toolbox related to addressing some of these energy challenges, whether they're directly attributed to data centers or a broader region-wide issues related to economic growth and environmental impacts. Let's go to the next chart. I think we'll pause there and see if we can answer some questions.
Hey, thank you, Alan. And perhaps Joel, you could take down the slides. As previously requested, if you have a question, please put it in the chat and I'll be able to ask Alan your question. And also the slides from today will be up on Northern Virginia Regional Commission's LinkedIn page. And the video of this recording, the recording of this video and the slides will be on NVRC's website tomorrow. So with that, are there any questions in the chat? Not quite yet. Let me start, Alan. Just really briefly, I did see that you started to talk about, renewable natural gas and opportunities for hydrogen use. Is that something that you're seeing trending in other places in the country?
Yeah, I think that the renewable natural gas movement is a fairly new topic for power generation, like the applications we're talking about, but it is beginning to get a lot more interest. It is what's known as a drop-in fuel. It can be easily used as an option to decarbonize existing natural gas uses. Historically, most natural gas that was renewable natural gas was used for transportation. Methane was captured, it was put into a pipe or even trucked off-site to be used for buses and other transportation uses. Those transportation uses are electrifying, and so the market for renewable natural gas is looking for new use cases, new applications for renewable natural gas. And we think that this resiliency microgrid application is one of the best. We can use the natural gas infrastructure to deliver the natural gas into the system. It offsets molecule for molecule fossil natural gas. And we can balance supply and demand, not in real time, but over longer periods of time. Hydrogen is a little bit different, and we have done successfully some testing of hydrogen blends, where the generators that I showed in those pictures today could use hydrogen blends if they were available either from the local utility or blended on site. But the cost of hydrogen is a little bit higher, especially if you have to store it on site in the form of either compressed or cryogenic storage. And I think that there's a lot of other uses of clean hydrogen that will probably suck up the available hydrogen before we need to store it for a few hundred hours of use a year. But we're ready for it if it were to come. If hydrogen blending was available from the local utilities, we'd be able to further decarbonize without having necessarily to use renewable natural gas in the long run. And then I should point out, Bob, that when hydrogen can be stored successfully on site cost effectively, we can repower one of our microgrids by replacing the engine inside those boxes, leaving most of the plant intact. And we can have 100% hydrogen engines so that we can use 100% hydrogen rather than just the blends that we've already tested to.
Okay, great, thank you. Dale, did you have a question at all? Oh, I do have a question here. 1 second. This is from Gene Wright. Renewable natural gas is a new term to me. Is frack gas used for the natural gas needed? Is there enough recovered methane gas available for renewable natural gas?
Let me go a little further into some of the renewable natural gas industry. There is a lot that is going on in the renewable natural gas space in the US. It's even more prevalent in Europe, where they have captured bio waste for a long time, and using capture techniques, they capture the methane before it can be released into the atmosphere, and they purify it. NREL, the National Renewable Energy Lab, has forecasted that we have enough technical capacity of renewable natural gas today to be able to displace maybe 15% of the current national natural gas use. There isn't any fracking involved. Fracking is really associated with fossil extraction. And depending on the basin, it is either a waste byproduct of oil extraction or perhaps the primary purpose of drilling. None of that applies to renewable natural gas. It's oftentimes it's a dome that goes over waste products that would otherwise be decomposing and emitting methane. You just use bio bugs, I guess is the best way to describe it, bugs in this waste stream, and it decomposes that waste stream and in a controlled way captures the methane before it gets released. Today, a lot of that ag waste just decomposes naturally and the methane is emitted. And this is a way of basically getting free gas, free in the feedstock's otherwise waste feedstock. The cost to process it does take some doing. And so it is at a price premium to fossil natural gas. I will add that we don't run very often and we're not as price sensitive as a lot of natural gas uses. So it seems to work.
Thank you. You see a lot of the black plastic domes in Germany and other places where they use feedstock from the corn stalks that they put in a pile and then put a dome over. I have 2 more questions so far. Wondering, can you explain more about what is needed to switch hydrogen engines versus fuel cell?
Sure. Fuel cell is a form of a hydrogen generator. It uses a chemical process. What I'm referring to in repowering of these systems that I showed pictures of is this would be a hydrogen engine block, a combustion of hydrogen rather than combustion of natural gas. We'd open up the access doors into our generator package, and we would remove the existing engine, and we would replace it in the same space in that block with a hydrogen capable engine. Usually that means a change in materials that can be able to withstand some of the corrosive properties of hydrogen. It would otherwise operate in a very similar way. There would be a combustion process. The emissions would be controlled to those same low levels that I described earlier. And the rest of the installation of the microgrid, things like the alternator, the radiator and cooling package, the emissions controls, the transformer, switchgear, cabling, concrete, all the rest of that would stay in place. And so we see a roadmap for decarbonization and conversion into hydrogen when it's cost effective to deliver pure hydrogen to a site. And we are maybe a few years away from seeing that become a reality. We may want to either have proximity to a hydrogen pipeline. Again, I don't think those are going to be very common in many parts of the country, or we would store it on site in cryogenic storage systems or compressed storage systems. They just take up a lot more space. And so it's pretty expensive for just a few hundred hours of operation.
Thank you, Alan. Another question. You mentioned that there's no water usage with these microgrids. Do they have any positive or negative impact on the surrounding water systems? And in parentheses, any discharge concerns.
Yeah, these are dry catalysts, what they're known as a dry catalyst emissions control. There's no water input because there's no steam that's being generated. And so the consumption of water is literally zero. I wouldn't say there's a positive impact, but there's no negative impact in negative use. Spilling of substances on the site might be also where the question is going. What we have is normal engine oil, radiator fluid, things like that. But our design of our generator has a catch basin at the bottom of each of those white boxes. And so 100% of the fluids in a generator, if there was a rupture of anything, a hose or line or gasket, it can all be contained on site. So the risk of spillage is quite low. Other generators have their own techniques for managing whatever fluids are used locally, but a lot of those SCRs do use water and or ammonia and other kinds of fluids in order to manage their function, and we don't require any of those.
Okay, here's a question here, a little bit long here. I've always been confused about the term microgrid. If you're not using battery storage or solar energy, how is the design of a gas microgrid different from a diesel generator plant that can feed power back to the grid? For data centers, it seems though microgrid providers are simply offering non-diesel fuel options.
Yeah, let's talk about maybe the definition of a microgrid. Broadly speaking, DOE has one, and the examples that you described are all microgrids. A microgrid is a defined boundary where there are electrical loads and electrical generation that can supply that load for purposes of an island operation, meaning no grid connectivity. It also should be able to be grid aware, meaning it should provide some level of interaction with the grid. A solar and storage project can be a microgrid if there is enough storage that can island that particular load center and operate in island mode for an extended period of time. Many solar and storage applications don't have enough storage to be able to island. And so a lot of solar and storage installations are not technically microgrids. A diesel generator that does not interact with the grid and it's just for backup is also not a microgrid. Usually they don't have the air permits to be able to provide grid services, and so they are not set up in a microgrid configuration. In our case, we have a grid synchronous interconnection typically so that we can operate in support of the grid or provide backup per the definition of a microgrid. So I think that microgrids are a lot of different flavors, and the ones that I'm describing are primarily for resiliency. Black sky conditions is another way of phrasing that can also support the grid, whereas a lot of other installations and even some microgrids are operating every day, but maybe can't provide island operation if the grid were to go down.
Thank you, Alan. Another question, how close to a natural gas transmission pipeline or distribution line would a data center or other use need to be in order to cost effectively consider your system?
It's a kind of it depends answer because the size of the microgrid can justify more capital expenditure to extend the lateral to the local gas supply. We're thinking in the data center space within a few miles is all that's necessary. It doesn't have to be on the street in front of the data center. It can be a few miles away. If there's multiple data centers that are in a region, we've had thoughts about pooling their aggregate demand and justifying a natural gas lateral extension to cover multiple properties, and they could share the cost in that.
Thank you, Alan. Any other questions for Alan? I don't see any, so thank you everyone for your participation. Big issue. I'm sure there'll be further discussion in Northern Virginia and other places in the Commonwealth about data centers. Again, this recording and Alan's slides will be on our website sometime tomorrow before noon. and they will be posted on NVRC's LinkedIn page, or for those of you who I'm connected with, on my LinkedIn page at 1 o'clock this afternoon. And all of Alan's contact information are on those slides as well. Alan and Joel, thank you very much for your time. Thank you for everyone who joined us today on this webinar. I'm sure that we will be hearing more about this issue for many, many more months to go. And we appreciate it. And have a safe day, everybody. And we appreciate your time.
Thank you all.
Thank you.
Thank you.